Bismillahirrahmanirrahim. In the previous video, we have seen that for this kind of dynamical systems in plane, we observe that the solution is given by x of t to be c1 times real part plus c2 times imaginary part of the solution that we construct in a particular way. Okay, so and in fact we also had seen that this real part in this case was cos beta t and minus sine beta t plus c2 times sine beta t, and this one was cos beta t, or I can write it c1 cos beta t plus c2 sine beta t, and this one is minus c1 sine beta t plus c2 cos beta t. Okay, so this one is the solution, or maybe you can write x of t and y of t. So from here we have x to be equal to c1 cos beta t plus c2 sine beta t, and also y to be equal to minus c1 sine beta t plus c2 cos beta t. That is, so this one is our x and this one is our y, and now it's not hard to show by using simple algebra that x square plus y square is equal to c1 square plus c2 square. What does this mean? This means that the solutions to this system where a was this particular are circles centered at origin. So solutions to this particular dynamical system, all solutions to this particular dynamical system are going to be circles centered at origin. So what is going to be the fixed point, and is it stable or unstable? In fact, for all of these systems, any kind of uh, this kind of system will have 0 0 as its fixed point. The only thing that is we need to check whether this fixed point is stable or unstable. But what we know from here that every trajectory or every solution that we have is going to be a circle centered at origin. But these functions are also telling that these are functions with the functions with the period 2 pi by beta. So from these two x and y, we conclude that the trajectories are going to be circled centered at origin like this. For example, this one. Okay, consider this is a circle, though it not looks like a circle. It more looks like an ellipse. Oh, forgive me for my crazy drawing. Oh no, so these are going to be the circles centered at origin. Okay, maybe we can raise it a bit more. So these are going to be trajectories are going to be circles centered at origin. One more thing, we have seen that for this system with this 0 beta minus beta 0, if beta is positive then these circles are clockwise directed. If beta is less than 0, then these circles are counterclockwise directed. So in this case, let's say if beta is positive, then the direction should be clockwise like this. Okay, so the circles are pointing in the clockwise direction for beta positive. Okay, so like this, like this. And if beta was negative, then they would have been pointing in the counterclockwise direction like this. Like this. But since beta is positive, we assume so, therefore the circles are oriented clockwise. So for this we will consider some of the example and see their plots on the phase portrait plotter. But don't forget that this kind of system where you observe circles like these, this kind of system is called center. This kind of behavior is known as center. And origin, what should be the origin? Is it stable? We can also observe that, we can observe here that the circles are getting shrink towards this 0 0. So we can say that this origin is stable. In fact, we can say that this is stable. So this is stable. Yeah, origin is going to be stable. For the center case, origin is going to be stable. So, and also we will call this Lyapunov stable, and the Lyapunov stability will be studied in the later videos. So let's take some of the examples. For example, we can study this example, x prime of t to be equal to 0, 20, minus 20, 0, xy. So the system is going to be, so beta is 20, so the system is going to be x prime to be 20y and y prime to be minus 20x. So let's see its phase portrait in the phase portrait plotter. So it's 20 times y, and then it was minus 20 times x. Let's plot it. So you can see that because beta was positive and it was positive 20, therefore the circles are directed clockwise. Let's see. So you can observe that these are the circles centered at origin, and you can see that these circles are ultimately getting towards origin. So the origin is in fact stable as well. So now what we can do is we can change the sign of beta and we can consider beta to be negative. Let's see. Now let's consider the beta negative. So let's say beta is minus 20. The system is going to be minus 20y and y prime to be 20 times x. Let's plot this. It sorry, it is expected to be counterclockwise. Okay, so let's see. So let's consider now. Let's consider this one, minus 20 times x and then 20 times y. So let's plot this. Oh, sorry, this was y and this was x. Okay, so you can see that now beta is negative and hence the circles are directed in the counterclockwise direction. Okay, so you can see this. Okay, so what's the summary of this all? Let's summarize it. We considered a particular system, which was this one, and it has purely imaginary eigenvalues. Okay, so in fact, origin is fixed point. It's not hard to show. One thing that we observed. Secondly, we have seen that the solution is going to be C general solution C1 times real part and C2 times imaginary part, and you need to see it in the previous video. And then we have seen that the trajectories are circles centered at origin, and we also, so it's like clockwise or counterclockwise depending on the sign of beta. And then we also saw that the origin is stable. What else we saw? But not asymptotically stable. Okay, further what we realized is, what was the point? Solutions were of periodic nature with period 2 pi by beta. In fact, the solution was x was equal to c1 times cos beta t plus c2 times sin beta t, and y was equal to minus c1 times sin beta t plus c2 times cos beta t. That is it from my side for this pure imaginary eigenvalues part. In the next case, we will be considering the systems where the eigenvalues are not only, like, the eigenvalues are complex. They will be involving both the real and imaginary part. Thank you.